The classic bridge question. So when we want to test you on quadratics or parabolas, we're like, let's use a bridge. In this case, it's a symmetrical bridge, right? And it's in the shape of a parabola. We're given some information about the towers, the distances, midway point, and we're given this vertical post, and it's 10 meters from the center. So if this is the center line, that is 10 meters. And the first question is to use algebra to show that the post, that dotted line, is 6 meters high. Awesome. So a few ways of going about this one. The first decision you need to make is, right, we have a bridge, great, but where is our, what's our coordinate system? Right, it's going to definitely be x and y because it's just 2D, but where is the origin? So there's a few, well, I'll let you have a think about some reasonable places for the origin, and I'll share my ideas now. So the mark scheme puts the origin at the center of the bridge, right here. So that's a pretty good spot, right below the vertex. Another reasonable spot would be at the tops of the towers, right, at the x-intercepts. Yeah, those would probably be the best origin spots. However, any would work if you had enough information to find the equation. So the mark scheme goes for the one in the middle, but let's go for this top left one, just to expose you to something different. Right, so this is our x and y. I'll just say that putting the origin here does make it a little bit harder, right? So that's good for practice. However, in an exam situation, spend some time thinking about what origin would be the easiest for the calculations. Awesome. So that means the center, let's just put the x-axis up here. So the center of the bridge is at 20 meters. And that means this vertical post is at 30 meters along the x-axis. And we're given, what else are we given? The height of the cable above the road is 3 meters here, which means on our axes, the vertex, right, the turning point here, is 15 minus 3, so 12 meters below. So that's at negative 12. Right, see why this origin is a little bit more confusing. We have a few offsets to deal with, but good practice. And the other x-intercept is at 40, right? So to start, we'll want to find the equation of the parabola, right? This parabola here. We know the x-intercepts. One is at the origin, so we will use x-intercept form. Just a reminder from the graphs topic, it looks like this. Right, where x1 and x2 are the x values of the x-intercepts. K is some scaling factor, right? It could be a tall and skinny parabola, or it could be flat and wide. So we know the first intercept is actually at the origin, so x minus 0. The second one is at x equals 40, so it'll be x minus 40. And just to simplify that a bit, we don't need to write x minus 0, we can just write x. Makes it a bit neater. And so that's the equation for our parabola. But now you'll notice we haven't worked out the scaling factor yet. So to work out the scaling factor, we need to substitute in a point. So substitute in a point, so an xy point, to find k, right, the scaling factor. So let's have a think. We could, what points do we know, right? We know the x-intercepts, but you'll find out if we substitute in the x-intercepts, these go to 0, So that's useless, right? Because we already used that information in constructing this equation. So we need a different point. The other point that we have is the vertex, right? So that in our coordinates, it's 20 across and then 12 down. So using the vertex, which is at x is 20, y is negative 12. So negative 12 goes in for y, 20 goes in for x, and we get negative 12 equals k times, what's that, 20 times negative 20 is negative 400. Now k equals negative 12 divided by negative 400. Let's just check. Oh, menu, run maths, 20 times negative 20, negative 400, yep. And so negative 12 divided by that answer, negative 400, is 0.03. Oh, running out of room. So putting that into our equation, so therefore our model is 0.03 x times x minus 40. All right, so we've characterized our model. And now to answer the question, we need to show that this post is 6 meters high. So to do that, we could work out this y value, right, when x equals 30. So putting that into our formula to get the y value. And then the difference between 15 and that should be 6. So putting in, wow, I'm really running out of room. Well, I guess I've elaborated on what I'm doing, right? That took up a few lines, so bear with me. So putting in x equals 30, we get y equals 0.03 times 30 times 30 minus 40. Putting that in our calculator, so 3 times 30. 30 minus 40 would be times minus 10, negative 10. That's minus 9. So that means this bit here, that minus 9. And if this goes 15 down, right, 15 here, and 9 here, or a distance of 9, that leaves us a distance of 6 for the post. So we'd just be like, what's a good way of writing that? Yeah, just 15 minus 9 equals 6. Now putting that into words, we'd say the bridge has a height of 15 meters. We subtract the distance from the top of the bridge to the cable, which is 9 meters, which leaves us 6 meters distance between the cable and the road. Right, so I'll let you just put that into a sentence because I ran out of room. In part 2, we have the same setup, so the same bridge, same distances, but now we're focusing on the outside parabola, right? The outside cable that is also parabolic. And we're looking for this distance C to D, where that distance is 6 meters above the road. So from the previous question, part I, we worked out that 6 meter post, so that at point C is, what is that, 10 meters from the center. So 10 meters from the center, that's 10 meters. Which means, what is this distance here then? Half of it is 20 meters, so that distance is also 10 meters. That's not to scale too well. Is that right? It must be. 20, 30, yeah. Wow, never trust a diagram, eh? So just to clarify that point, so from the previous question, we already know the x location of C, right? It's 10 meters to the right. of the vertex, which means there's a further 10 meters until the vertical post. So it has the same dimensions as above, yep. And we're looking for this distance C to D. So we're going to need to find this horizontal distance right here, right, and add that to 10. So what do we need to do first? We need to find the equation of this parabola, because once we have that, we can put in the y equals 6 value to then get this x value to then work out the distance. So it's very similar to part I, but just a different parabola. So we could use the same origin all the way over here. That seems a bit wasteful to me. It would be much easier if we just move the origin, let's say, onto the vertex, or even up here. There's pros and cons of moving the origin. The pro in this case is it makes the calculations a bit simpler. The con is keeping the origin consistent is often better for longer problems, right, when you need to refer back to the origin. But here, it doesn't actually matter because we can just write down the absolute distances, like I've done here, those 10 meters and 10 meters. So let's pick the origin at B, the vertex of this parabola, so x, y. So let's use vertex form, which is y equals k times x minus a squared plus b squared, where a and b are the coordinates of the vertex. In this case, the coordinates of the vertex at B is actually the origin, right? Because we picked the origin to be on the vertex. So this simplifies down quite nicely to that. And of course, we don't need to write all those zeros. So that's just kx squared, all right? Which is a standard parabola, x squared, but that's been scaled by k. Now we need to find k, the scaling factor, using a point that lies on the parabola. So looking here, we have this point up here. That could be good. Now we need to take it from our new origin. So how much to the left is it? Is it 20? No, we've got to be careful. So this 60 is this whole distance, which means there's a distance of 10 here and a distance of 10 here because it's symmetrical. So 10 meters there, 10 meters there. Right, it's easy to think that would be 20. Believe me, I literally just made that mistake. That's why I'm refilming this video. But it's not, it's 10. So this point is 10 meters to the left and then 15 meters up. So 10 to the left, so x is negative 10, and 15 up, positive 15. So we'll use that point to solve for k. So substituting in y for 15 and negative 10 for x, we get k is equal to 15 divided by negative 10 squared, which is 100. Which is, as a decimal, I should have done that in my head, 0.15. Yep, there we go. So therefore, y is equal to 0.15 x squared. Right, that's the model for this parabola on the side here. Now we can use that model to find this x value, right, in line with D. And that happens when y is equal to 6. So substituting in 6 for y, dividing both sides by 0.15, and then square rooting, we get x. So 6 divided by 0.15. Now square root 40. So we get plus or minus 6.325 or 6.32. I can kind of just ignore the negative solution because we're using distances here. So that means diagrams zoom in, enhance. This distance is 6.32, right? Because we worked out the x value here. The distance we are after is C to D. So that's the 10 meters plus this orange bit. Right, that's CD. So overall, it has a distance of 20 meters, right? Not to scale, but 20 meters. And we're subtracting from that 6.32. So 20 meters minus 6.32. Come on, you can do it. It's had a rough day, this laptop. There we go. So CD equals 20 minus 6.32, which equals 13.68 meters. So to recap this one, we picked a new origin, in this case on the vertex of the parabola we're looking at. We then found the scaling factor k by substituting another point. We then found the x value that corresponded to y equals 6, right? So we could get in line with D. We then reasoned about the different dimensions, just being careful about things being to scale, and that this 60 is actually all the way across. So we're not making the same mistake that I did.